All right, perfect. Thanks. So, good morning from me. I'm Ioannis Faros, and I'm a PhD student with Dr. Tanner at the University of Delaware. And basically, today I'm going to present you our work on differential flat systems, and I'm going to answer this question: Can autonomous surface vehicles be differentially flat? So the answer to that question is, of course, yes. Autonomous surface vehicles can indeed be differentially flat, of course, under the appropriate physics model, but states and inputs may not be in an explicit closed form. And we're going to see why this actually statement holds. But before that, let's see what people are using in the literature to model autonomous surface vehicles kinematics. So basically, in the literature, you can find the standard ship kinematic model that is not other than this. And this kinematic model, of course, has four states: x, y, theta, and v, standard kinematics, and one constraint on the sway velocity to control inputs. However, this kinematic model appears not to be differentially flat. And the problem with this model is actually this term here, and especially the coefficient gamma, that actually messing up with the recipe as you try to derive the differential flatness property on this model. It appears that this term cannot be cancelled, and it messing up with our recipe. On the other hand, though, we have the hovercraft kinematics, which basically are the same with the ship model. And that's very interesting because hovercraft, appears to be differentially flat. And appears to be differentially flat because this term here has gamma equal to 1, meaning that actually we take the kinematic model of a ship, we force gamma be equal to 1, we choose it if you want, and we can prove that hovercraft is differentially flat. However, we believe that if we had an appropriate model and we could actually, let's say, play with coefficients and the relative degrees of this model, we could yield gamma equal to 1 and not force it. So to do so, we consider a marine vehicle as a slender body. And a slender body means that the length of the vehicle is much, much larger than the width. We place, of course, a local frame B on the body in the midship as standard, and we yield, of course, the same kinematic equations. However, when we try to derive the constraint on the sway, we looked at the marine hydrodynamics of Newman. It's some principled book from marine hydrodynamics. And if you take the surface integral along the hull, do some simplifications, you can derive actually this very, very interesting equation. So this equation has, of course, the two terms that both ship model and hovercraft have, UR and the drag. But now, instead of gamma as a coefficient, we have this very, very interesting coefficient, this very, very interesting added mass coefficient, which essentially depends on xt. And xt is the coordinate of the stern, means of the back of the ship, along the xb axis. And now we have the freedom actually to play with this term and make it equal to 1, because we want essentially to cancel this UR term as we do in hovercraft. However, we have also this term here, UV, which essentially adds a non-linearity in the system. And this term basically is the effect of the pure translation, the pure steady translation of the ship on a direction that is not the symmetry of the ship. So what we did with this derivation, what we have actually with this constraint on the sway is that now we can choose the location of the origin of the framework of the frame, and we can essentially match the added mass coefficient with a mass. So we take the origin, we put it on a place along the xb axis, we match the coefficient of the UR with M, and now we can have the coefficient equal to 1. So we not force it, we not choose it as we do in the hovercraft, but we make it as we choose the origin of the local frame. So essentially, we align our model with a model of the hovercraft, and we can derive differential flatness property, but the derivation is different because now we have also this term here. And given on this model, we have the following proposition. So we have the new physics-based model, same kinematics as the previous models, a different constraint on the sway that would matches somehow with hovercraft, but at the same time we add some non-linearity. And we say that this system can indeed be differentially flat with flat outputs x and y. And of course, the states and the, let me see, the states and the control inputs can be a function of the flat outputs, but they are not in an explicit form because now we need to solve a quartic polynomial, meaning a fourth order polynomial, each time step to have an expression of the flat outputs regarding to the states and the inputs of the model. So given that we prove that our new model is differentially flat, of course, we can create the linear system from a chain of integrators, and now we can design a trajectory tracking controller that can be, of course, translated to the original model. And I have some simulation results in the next slide. However, I would like to point out that there are two challenges and one advantage of this work. So the first challenge is that the states and the control inputs are not in an explicit form of the flat outputs because at every time step we need to solve a fourth order polynomial, which is kind of hectic, obnoxious, but it works. And the second challenge is that the control input R and the control input U do not share the same relative degree, meaning that the control input R actually has the highest derivative of the flat outputs, and this do not match with U. So there are some techniques that we can use to match the relative degree. One of them usually is input extension state. Oh my God, I'm missing the word. But anyway, anyhow, is not working. I mean, you can take the control input U, you can make it as a state, you take the derivative, but it's not working because it appears to have the R in the expression, and it's like you're trying to chasing your tail because every time you are taking the derivative of your control input, you cannot share actually the same relative degree. So we can use some rigid body kinematics to basically decouple the R and the U expressions. On the other hand, we have one advantage, and this advantage is essentially that we can take all the derivatives of the flat outputs from sensor measurements. So if we have like a DVL, we can take the surge and the sway velocity from measurements, and this actually makes the implementation much easier. And now, as I promised you, I have two simulation results. Basically, we designed a trajectory tracking controller for a circular motion and a figure eight motion. We had two different, of course, initial conditions of these two trajectories, and in each trajectory we see that the vehicle actually achieves to catch the desired trajectory that we gave to the model. So that was my presentation. Thank you for your attention, and I'm gonna be happy to answer any of your questions.
Thank you, Ioannis. So anyone with question there? I don't see any raised hand. Loic.
Yep.
Loic, go ahead.
Hi, can you hear me? Yeah. Okay, thank you for the presentation. It's a topic I've been working on for a while now. This question actually, I mean, your answer to this question actually goes against some of the work of Professor Sierra Ramirez. Is a famous book, and so I was wondering, watching your presentation, if your approach, notably with the polynomial roots for z high, could be applied to different kinds of non-flat or maybe almost flat systems, as the USB can be. You have this class of Liouvillean systems, and USB is one of them. Do you think we could apply your methods to these other Liouvillean systems?
So, for example, the SIP model that I showed you, the kinematic model from Niemeyer, I believe the name is, which appears to be a Liouvillean system. I believe that you can apply the same process as we do. We haven't tried that yet, to be honest with you. Essentially, the quartic polynomial, how can I say, like, is we achieved the quartic polynomial by doing a trick. So we use some trigonometric expressions to have the angle in an explicit form, in a transsential form, actually. And we yield a fourth order polynomial that the roots of the fourth order polynomial essentially will give the angle, the theta, I mean, the state theta. So for the SIP kinematic models that I showed in the slides, the first ones, probably we can do the same process, and probably we can prove it's differentially flat, but I'm not sure for other systems or if this thing can be generalized.
Okay, thank you.
You're welcome.
We have a question from Luc Cholin.
Yes, thank you. So I have a small question. First, in your title, you have autonomous. Why autonomous surface vehicle be flat? Why you said autonomous? As soon as you are autonomous, you don't have any more inputs. Probably you mean surface vehicle only, no?
I mean, autonomous surface vehicles, we mean like robots. I mean, where you can have inputs. I mean,
okay, it can be a boat. Non-autonomous. Okay, so it can be. And my other question is, flat output you consider is always the position x and y?
For our derivation is x and y.
Okay, always.
You can consider whatever flat outputs you want. It's not a specific choice, but for x and y, it works for us.
Okay. Thank you.
Of course.
Loic, you have another question?
Yes, I do. But I mean, we can like do this afterwards or on our side if we are on a time crunch.
We still have 5 minutes. You can put your question.
Yeah. Okay. So my question is, did you try to actually look for different flat outputs instead of moving the frame, like the mobile frame, on the vehicle? Can you just change the flat output and use some off-center point?
So for that system, for the new system, because we added also the nonlinearity, the UV, I think yes, we tried to use other flat outputs, but it didn't work. So we wanted actually to match the system with the hovercraft, where we know that it's flat, and maybe see some cancellations, as we saw the UR term essentially is getting cancelled during the derivation. But yeah.
Okay. Okay. Thank you.